Hello everyone, my name is Swayamtrupta Panda. I would like to thank the organizers for giving me this opportunity to present the recent results of our research on optical iron 2 and near-infrared calcium 2 emission in active galaxies. So here I'm showing iron 2 pseudocontinuum. Why pseudocontinuum? Because iron emission is formed in terms of blended multiplets, which mimics such that of a real continuum. As you can see, many authors and groups have tried to devote their time to study the effect of the iron emission and understand it both from theory and from observations. And here I'm marking in the box the portion of the iron emission that is used for the studies of quasar main sequence. That is that optical part between 4434 to 4684 angstrom. There are over 300,000 spectral lines ranging from the ultraviolet to the infrared, which makes this the study of this ion, quite challenging. So in order to negate of sorts this complexity that gives rise from the iron studies, this was the main motivation behind this introduction of the project, CaII project. To give you an idea how different and how complicated the iron emission is in terms of calcium, it's in terms of iron optical emission, we had over 1,500 lines to characterize, while we only need the 3 lines of calcium in the infrared, which I'm marking here in the spectra, that are required to characterize the same amount of emission, or at least match it up with the iron emission, which is as complicated as 1,500 lines in just the optical part. Now, when I say calcium emission, this refers to the calcium 2 triplet emission, that is the near-infrared triplet, as I showed in the spectra, between these 3 wavelengths. And prior photoionization modeling have suggested that indeed calcium emission does form in dense and low ionization regions similar to that of iron, and thus can be used as an effective proxy. But we took this a step further and tried to characterize both from observation and from modeling whether this is indeed the situation at play. For that, we took in an observational sample, and our sample consists of 58 sources that has been taken from literature containing both optical and near-infrared spectral information. Moving on, so the major part of this study was to understand the emitting regions of these 2 mediums, and for that we utilized cloudy simulations by varying cloud parameters and ionization. We utilize an observed SED for our Zuki 1, the prototypical narrow line Seyfert 1 galaxy. So this is the cutout of the photoionization grid that we have computed using cloudy, which is basically governed by the photoionization theory, which is marked over here in the top. Here the U represents the ionization parameter, which is given as the number of ionizing photons as a function of the cloud density. On the left-hand side of this picture, we have a cutout of the log U and log N parameter space, which is color-coded by the ratio of the calcium triplet over H beta, which we call the RCat, and a corresponding diagram on the right is given for the RFE, which is the iron emission over H beta. And this red line over here marks the distribution of the clouds, which is only considered inside the broadline region, which is non-dusty. And as we can clearly see, the maximization or optimized emission of both these species occurs at more or less the similar values of densities and ionization parameters. This neatly ties down to tell us that the size of the emitting region for both these species are kind of coexisting. But we do not stop here. What we do with our modeling is we consider 5 different cases of the models, starting with the baseline model, which considers the cloud to be of solar composition and the cloud sizes estimated by the column density 10 to the power 24 centimeters per square. We also take into account different distribution of compositions and different distributions of cloud column densities in order to count the questions: what is the effective metal content and effective cloud sizes that could give rise to the optimum emission of both these species. On this picture here, right, which I'm showing on the right side, we overplot the observed sample of the 58 sources in solid symbols, and on the backdrop we showcase the results from our photoionization as a distribution in terms of ionization and densities. As we can clearly notice that the distribution really amplifies and covers the plane of the observed correlation. And to add to that, the correlation is such robustly predicted both from the observation side and from the simulation side. To summarize, we compile an up-to-date catalog of 58 sources which have corresponding RFE and RCAT measurements and derive the best fit correlation between these two species. By analyzing with respect to the photoionization modeling, we realize the maximum emissivity of both these emissions can be neatly tied down with respect to the two major quantities, ionization parameter and the broadline region cloud density. But what is also important to understand is that these models and these emission line estimates can be greatly emphasized in terms of the metallicity, that is the broadline region cloud composition, and the column densities that realizes the broadline cloud sizes. This work has already been published in the FeII, and I mark here the archive link for people for further consideration.